In this video, we're going to talk about section 4.6. Now for us, section 4.6 is optimization problems. Now often Calc 1 students have heard something about optimization problems before they get to this section, especially if they've talked to anybody who's taken Calc 2 at this point, i.e. a Calc 1 survivor. I'm not really sure what it is about optimization problems that drive people nuts. It could be the fact that they're word problems, but I would think by now, hopefully we've kind of outgrown that. I mean, after all, making a peanut butter and jelly sandwich is a word problem, and seem to enjoy those quite well. I guess now that I started to say that, not all of us enjoy those, right? If we have a peanut allergy. So for those of you with peanut allergies out there, I apologize for that. So let's get off that awkward 2020 moment and just move right into optimization problems. So what is an optimization problem? An optimization problem is a word problem. It describes a situation where we're trying to optimize something. Maybe we're trying to optimize the area that we can enclose with some fencing. We're going to start with that example. It's a classic first example in most calculus books. Maybe we're trying to optimize the cost of manufacturing a product. That's another classic example. Maybe we're just trying to maximize the area inside a semicircle. It's one of those problems that us teachers love to put on a test, and you students tend to look at it and go, why am I being asked to do this? So what do we need to know about an optimization problem? Well, we're going to make use of what we've already learned about the first derivative test to solve optimization problems. Optimization means to optimize. We're trying to find the maximum in the case of the area, or maybe the minimum in case of the cost of manufacturing. So we're looking for either a maximum or a minimum when it comes to an optimization problem. Which one am I going to find? Well, to be perfectly honest with you, most of the time you only get one critical value. You may have to check the endpoints based on our closed interval method if there is a closed interval that defines your function or that defines your situation. But more often than not, we only end up with one critical value. In the books that we generally provide to you, there's just one critical value in most optimization problems. So what we want to do is we want to make sure that we follow through and we check our critical value to make sure it is indeed a maximum if we've been asked for a maximum, or if it's indeed a minimum if we've been asked to find a minimum. So let's do what all of us calculus teachers do when we start optimization problems. Let's start with an example. We generally cover the strategy while we're talking about an example. So we're going to start with a classic example here. I'll read it to you. We'll write down some information. But first, let me just read the problem to you. We have a farmer, and he has 2,400 feet of fencing, and he wants to fence off a rectangular field. Now, that's a typical optimization problem. We have a set amount of a product, in this case fencing, and we want some kind of task. In this case, we want to make a field that's a rectangle, and we want to optimize the area. No use taking our fencing, 2,400 feet of it in this case, and making a field that is, infinitely, well, we can't infinitely, we got 2,400 feet of fence, but we can make a field that maybe goes 1,200 feet down, 6 inches across, 1,200 feet back, and 6 inches down. And of course, that's going to take 2,401 feet of fencing, but you understand what I'm saying. That field would look ridiculous. We want to find the optimal size of a rectangular field. Now, in the case of the problem we're giving here in this first example, we have an additional situation. What we have is we have a river. Our farmer is lucky enough to have land right next to a river. And so what he's allowed to do is he's allowed to fence in a rectangle using the river as one side. So his fence is going to come down this way and then go like this and then come back over this way. Now, the problem's changed up a bit because of the river, right? We have this dimension, and only the length one time. So what do we know? Well, we can sit here and just start guessing, right? We can guess. We know it's a rectangle. We can say, well, I'm going to make this 100, and I'm going to make this 100. That's 2,400 minus 100. Remember, we have 2,400 feet of fence, right? Of fence. can sit and guess. We can say, well, if I put 100 here and 100 here, that's 200. That leaves me 2,200 feet to run lengthwise. Or, you know, I can make this 500 feet and 500 feet, and this is 1,400 feet. The problem is, every time we make a guess, we'd have to recalculate the area of the field. And what we want is a straightforward, precise, hopefully simple way to maximize the area of that field. So we are going to employ calculus in this case. That's what we're going to do. So what I would suggest is you write down your given and you draw a sketch. Sketches are highly important in optimization problems. They generally are required by most instructors. And the reason they're required is because without them, the problem becomes a lot more difficult. So what do we know about our fence? Well, we know we can call this side of the fence over here x, and then this side over here is also x. It's a rectangle, so those two sides are equal. Then we'll call this side y. So we have a fence right now that is x by y by x. Remember, the other side over here is a river. We don't need anything over here at a river. Apparently, whatever kind of livestock we're putting in this enclosed region is definitely afraid of water. So I guess we are literally herding cats. So where are we going to go with this? Well, we want to maximize the area. So my suggestion is you write down the given, and you write down what you're supposed to do. You want to maximize the area. Right? Now, how am I going to do that? Well, what are we going to do to maximize the area? We're going to find a function that describes the area of our field. Usually, these shapes that they give us are pretty straightforward, and we can usually use some of our elementary school, junior high type formulas to come up with a formula for the area or the surface area or the volume. In this case, it's just area. And the area of this, of course, is going to be length times width because it's a rectangle. So our area would equal x times y. Now, we know what to do to maximize that. We're going to take the derivative of both sides, set it equal to 0, find our critical numbers, test those critical numbers, see which one of those critical numbers gives us some maximum. And because we have a closed amount of fence, we have 2,400 feet of fence, we could actually test the endpoints if we had to. Herein lies the rub of optimization problems. When we take a look at our formula right here, which says area equals x times y, the problem we have is this is two variables, x and y. We're not in a multivariable calculus class yet, so we need to eliminate a variable. That's the big idea that a lot of people find mildly challenging, I'll say, with some optimism. So where do we go from here? We want to eliminate a variable. Now that is very typical on an optimization problem. Most of the time we're going to end up with a function that we can find pretty easily. Where we're going to have ourselves a little bit of difficulty is when we try to take the derivative. We're going to look at this and say, well, what am I going to do? Now, to be perfectly honest with you, you can do this with implicit differentiation. I'm not going to cover that in this video. I'm just going to talk about eliminating a variable. I think it's much more straightforward, much more, I don't want to say simple, but a much more understandable way to solve these problems. So I have to eliminate one of these two variables. Now, how do I do that? Well, we're going to eliminate a variable using the given. Now, what do I mean by the given? I mean the given information. We've been given a piece of information. Over here, we've been told that the fence, the amount of fence we have is 2,400 feet. If we take a look at our picture, that 2,400 feet of fence has to go from this edge of the river to this corner. Then it has to go from this corner all the way to this corner, and then it has to run back to the river. What do I mean by that? I mean right now, we know that 2x's plus 1y has to be 2,400. That we know because we have 2,400 feet of fence and we have to cover an x, a y, and x in terms of the dimension of our field. From here, we can eliminate this y by solving this equation. This equation says y equals 2,400 And that's what I mean when I say eliminate a variable. We have been able to eliminate a variable. We are going to be able to take this expression for y, place it back over here. I'm going to use a for area. And we're going to get x times, instead of y, we're going to have 2400 minus 2x. Now we have an expression in one variable. This is what we want. Our goal is a single variable expression. When we get there, that's when we know we have made progress. That is what we must do prior to taking the derivative. Now we're going to take, well, before I take the derivative, I'll go ahead and multiply this out because, I passed algebra and so I want to use it. So if we distribute there, we get this. Polynomial is much easier to take the derivative of, and we end up with a prime equals, and what do we get here? The derivative of 2400x is going to be 2400. The derivative of negative 2x squared is minus 4. And you saw that, I almost made that a 2, didn't I? Minus 4x. Now what are we going to do? We want to find a min or a max, and we know how to find a min or a max. We're going to find the critical value. Right? We're going to find the critical value. Now, in an optimization problem, it's very often the case that there's not going to be a point that's going to cause our derivative to be undefined. After all, we're doing an optimization problem. We're talking about something in the real world. Most of the time here, we're going to come up with solutions that do not result in an undefined outcome. So I'm going to take this, I'm going to set it equal to 0, right? That's what we said last time in my last video. I said I like to do it like this. Say, I'm going to set a prime equal to 0 over here. And so we're going to have 2400 minus 4x equals 0. That gives us, of course, 2400 equals 4x. Or we get x equals 4 and 2400 is 600. And so our proposal, right, right now is for one of our critical values is to be x equals 600. Now, it's the only critical value we have. It really makes no sense to ask ourselves, when does a prime fail to exist, right? That doesn't have any application to the story that we're telling here about the farmer, his field, and the river. So over here, we're just going to pass on that. So we have a critical value of 600. Now, what are we going to do with that critical value? Well, the problem asked us if we would have gone through the entire problem. The problem says, find the dimensions of the field that maximizes the area. Now remember, this is just a critical value. We do not know this is a maximum at this point. We have one critical value, and we have also the ability to say, well, how do I know that's a maximum, right? Well, we have a closed interval method. We can use the closed interval method here. We know that there's two extremes here for our fence, right? We could say that, 0 is a possibility, or we could say that 1200 is a possibility. But we're just gonna for the benefit of just moving on, trying to get as many things done in this video as possible and not drawing it out for any more time than we need to. What are we going to do, right? We're going to say, well, what happens? What is the area I get if x is 600? We have a formula right here, right? We have a formula here for the area. We have a formula here for the area. We even have a formula up here for the area. Because if x is 600, we know that y is equal to 2400 minus 2x, right? So what do we get there? We get 2400 minus 2 times 600, or we get y equals 1200. So our job here is to find the area. The area then, if that's what they ask. If they ask us for the dimensions, we're done. We have the dimensions. We're going to have 600 feet here. We're going to have 1200 feet over here. And we're going to have another 600 feet on this side. But what they really asked us for in the problem is to find the actual area, the maximum area. Well, now we can find the maximum area, and we can multiply 6 times 12. So the maximum area here for our problem is going to be 600 times 1200, and that's going to give us 6 times 12 is 72, and then we have 4 zeros, so we're going to get 720,000 square feet. Right? That's the maximum area for our feet. So that's our first look at an optimization problem. It's a very straightforward example. Didn't have too many bells and whistles, too many bumps or grinds in there. So I'm going to go ahead and erase this, and we'll take a look at another situation. Hopefully we can keep this, right? We can keep this as our description of how to do an optimization problem, and we'll just kind of follow this as our recipe. So let me get this erased off here. Get rid of the river. And we'll take a look at another optimization problem. What else could an optimization problem look like? Well, they come in all kinds of flavors. When you look at the homework problems in the book, there's typically 25, 35 of these things. We don't assign that many because usually you get the idea after a few of them what you're doing. But I'll do probably 3 or 4 examples here, and then we'll call it a close to the video, and hopefully you can go out and attack your homework assignment and have some success. So the next problem we have is we're talking about, we're going to try to minimize costs. Right? Our next example is going to be to minimize costs. And another classic optimization problem. We're trying to manufacture a product, and when we manufacture a product, we would like to keep the cost of the product to us on the manufacturing side as small as possible. So this product says we have a cylindrical can. So we have a can, right? We got a cylinder here. Got a cylindrical can, and we have a volume that we know we want to have for this can. So we know that the volume of this can is going to be 1 liter, right? So the volume is 1 liter. Right? So we want to make a can that holds 1 liter of liquid. And we want to find the dimensions that minimize the cost of manufacturing a can. We'll say our can is made out of metal, so we want to find the dimensions that minimize, right? Don't use maximizing here. Now I'm going to write max, so let's cross that out. That minimize the cost of the can. Now we can build all shapes of sizes of cans that hold 1 liter. Our can could be really wide and really narrow, really short, I guess is a better word there. It could have a huge radius and a small height, and that's probably not going to be the most marketable can that we could build. It might be novel in the sense that everybody would know about our can, but people would not be happy trying to store our can in their cabinet, or stores wouldn't be happy trying to put our can on their shelves. So we need to think about trying to minimize the cost, and we want to find the dimensions that minimize the cost to us. But keeping in mind, we want our can to look somewhat marketable. Luckily for us, this is just a calculus class. We don't have to worry about the marketability of our can. We're going to come up with the dimensions. We'll let the marketing people deal with that. So how are we going to go about doing this? Well, we're going to have to figure out how much material we're going to use to build our can, right? Our can has 3 pieces. If you think about the way you make a can, the can's going to have a top, right? There's going to be a top to the can. There's going to be a bottom to the can, right? Which is going to be exactly the same size as the top. So those are both a circle. So when it comes to thinking about the amount of material that we're going to use, we're really trying to find the surface area of our can here. So we're going to have the top, and we're going to have the bottom. Now, we're going to describe that in as area, right? We're going to say the area of our can is equal to, now we're going to have 2 of those, so I'm going to go ahead and put a 2 down, 1 for the top, 1 for the bottom. That top is a circle, right? It has a radius, r, And so if I had the radius of that being r, I know the area of the top. The area of the circle is pi r squared. So I'm going to have pi r squared here, or pi r squared here. So I'm going to have 2 pi r squared. So right now, the area of our can is made up of 2 pi r squared, one variable, the variable being the radius. Great, we could move forward, except we haven't taken into account the fact that there's more to a can than the top and the bottom, isn't there? We've got to worry about this part of the can right here. You know, I'll call it the side of the can. What do we have to do? Well, we need to think outside the normal paradigm of just looking at the circular can. We need to ask ourselves, what shape is that? What does the side of the can look like? I realize if all we have is the side of a can, it's a cylinder, right? It's a hollow cylinder. But what happens if we cut down the side of this cylinder and we unroll the can? If we do that, right, we're going to get a shape that looks like this. This is what we're going to get. This is a shape we're going to have. The side of a can, when you unroll it, makes a rectangle. And so we're going to have enough material to make the top of the can, the bottom of the can, and the side of the can. And now we need to come up with a dimension for this. Well, if we visualize what we have here, now unrolled down here, this is going to just be the height of our can. We haven't come up with a letter for that, so I'll choose H there. Now, what is this going to be, right? What dimension is this going to be? Well, if we look back up here on our can, that's going to be the distance it takes us to go all the way around the can. Now, we have a measurement for that, right? We call that the circumference of the circle. And we know the circumference of the circle is 2 pi r. So when we want to find the dimensions of the side of our can, we're really talking about a rectangle. So when we do optimization problems, the sketch is really important. I mentioned that in the first example. It's proving to be the key to getting anywhere with our second example here. So what do I know then is the area of this? Well, it's a rectangle, and we know area is going to be length times width, which in our problem here is going to be 2 pi r h. Now, if we attach that to our formula over here for the area, we get plus 2 pi r h. And our formula that only had one variable a second ago, and we liked it when it had one variable because one variable is what we're looking for, right? We always want to get, our goal is to get that expressed as one variable. Well, if we look right now, we have two variables. We have r and we have h. Of course, pi is a constant. So what are we going to do? We're going to eliminate a variable. That's what we're going to do. We're going to set out, we're going to eliminate a variable. And how are we going to do it? We're going to do that exactly like we did it in the previous example. We're going to take the given that they provided us, right? The volume is supposed to be equal to 1 liter. And we're going to look at the volume of this, and we're going to say, okay, the volume of this is supposed to be 1. Hopefully, if the volume is going to be 1, I can use that then to solve for one of those two variables. Now, they've given us the volume here as 1 liter, right? 1 liter. But we have to pay attention to the dimensions that they've given us for the can. This happens a lot in the optimization problems where we have dimensions and they're not always uniform. They're not always given to us in sometimes they like to give us one side in feet, but they give us the other side in yards, for example. So we have to be careful. 1 liter, that's a volume measurement, right? That's a measurement of volume. We need to convert that into a unit that we can use over here. Now, 1 liter, right? 1 liter, in case you don't remember your metric system, 1 liter is 1,000 cubic centimeters. Okay? 1 liter is 1,000 cubic centimeters. So, where are we going to go? How are we going to solve this problem? Well, we're going to have to get rid of, right? We're going to have to get rid of one of these variables. I think h is probably going to be the best one to get rid of, right? So, what are we going to have to do to get rid of that h? know what the volume of the cylinder is. We'll do some scratch work down here at the bottom. Hopefully we won't run into this. We'll follow down here to show ourselves scratch work. What do we know about the volume of a cylinder? Well, we were taught in geometry, right? That's a prism, so it's a regular prism, so it's a right prism. So we know the volume is area to base times the height. That's what we were taught. So the volume here is going to be area to base pi r squared times the height, h. Our volume is 1,000, right? We've got that. We've got pi. We've got r squared, and we have h. And now we have a pretty simple equation. We can solve this for h. If we solve this for h, we get 1,000 divided by pi r squared equals h. And now we have a candidate. I guess we got kind of big with our bubble there. I wasn't as optimistic as I should have been, was I? So we can just get rid of that, close that in here. We can go back up here and we can rewrite our area equation in terms of, well, now it's going to be in terms of just r. So what do we get? We get area equals, we have our 2 pi r squared, right? That's our top and our bottom, plus, and now we have 2 pi r times, and now for h, we have 1,000 divided by pi r squared. Now that will simplify to 2 pi r squared plus, and if we multiply the top out, we get 2,000 pi. Well, if we work ahead, right, this pi takes care of this pi, and so we don't even get 2,000 pi, do we? We get 2,000 divided by, this r cancels one of those r's, and we get 2,000 divided by r. Now, we've gotten to where we were hoping to be, right? Only one variable. So, where do we go from here? Well, we know where to go from here. We're trying to optimize. We're trying to find a minimum or a maximum, in this case, a minimization of the cost if it can. So we're going to try to minimize the surface area. And how are we going to minimize the surface area? We're going to take the derivative of this instead of equal to 0. See where it fails to exist. So what are we left with? We have a prime equals, we take the derivative here, right? Remember 2 pi is a constant, so we're just going to take the derivative of r squared. That's going to give us 4 pi r to the first power. Now over here we have, right, if we just jot this down, this is 2,000 r to the negative 1. We're trying to take the derivative of that, aren't we? And if we do that, what do we get? We get minus 2,000 r to the negative 2. Okay, minus 2,000 r to the negative 2. So what is that going to look like, right? Well, write it down, see how this is going to work out. So we get minus 2,000 all over r squared. Okay. Now we want to find out, right? Our goal is to figure out when this equals 0 or fails to exist. So I'm going to go ahead and simplify this. Right? We're going to get a common denominator here. The common denominator is going to be r squared. And if we do that, what do we get? We get 4 pi r cubed minus 2,000 all over r squared. So once we have our derivative in terms of, right, let's go back again, we write our function. We don't care how many variables there are. We don't get worried. We just look at the function, we write it down, and we have confidence that we're going to be able to eliminate the variables. We know the given is going to allow us to eliminate the variables. And so we proceed. And so we eliminated the variables. We got our expression in terms of just r. We simplified it. We took the derivative of that because we know we're looking for critical values, because critical values are the locations, right? Those are the possible locations for maximums and minimums. So where do we move from here? Well, we have our derivative. We have it written here. And now we're going to have to answer those two questions we always answer. When does a prime equal 0? When does a prime fail to exist? Right? Those are the two questions. Now this is a fraction, right? Fractions equal 0 when the numerator equals 0. So we can rewrite this as 4 pi r cubed minus 2,000 equals If we move the 2,000 over here and divide it by 4, we would get, well, let's just do the whole thing at once. We would get r cubed equals, we've moved the 2,000 over here, it became positive 2,000. Then we divided by 4, it became positive 500, and then we divided by pi, and so we got 500 divided by pi. And so r is equal to the cube root of 500 over pi. Not the best answer, but it's an application problem. In the real world, we would just grab a calculator, work that out, we would be able to tell the manufacturing plant, this is what we want the radius for our can to be to minimize cost. Now, we haven't paid a lot of attention to this. We didn't even have it as an opportunity to analyze in our previous example, but we do have a fraction here, right? And fractions fail to exist when the denominator is equal to 0. So we could say a prime fails to exist when the denominator equals 0. So that would cause us to set this equation up and we would get r equals 0, and then we would realize this makes no sense. Right? I mean, it makes no sense. What are you going to tell somebody? Hey, I want a can that holds 1,000 cubic centimeters, 1 liter of liquid. By the way, I'd like the radius of the can to be 0. No, that's not an opportunity. So what would we have to do now to verify that this really is a minimum? There's some more work to do. What would we have to do? Well, we would have to run a Sine Test on this, right? We would have to take this number, look at numbers less than this, and then look at numbers greater than this. We would have to generally just work out a Sine Test like we've done in the past. We know our critical number. Our critical number is the cube root of 500 over pi. Right? That's 500 over pi. And then we would put our terms of our factors over here. We would have 4 pi r cubed minus 2,000 right here, and we would have r squared here, right? And we would know for a number smaller than this, we would get a positive for r squared because r squared is positive. So if we pick a number here, we put an r squared, we get a positive, we get a positive here. So it's going to come down to this. Now this is a 0 of this. We all know that. So if I pick a number bigger than this, right? If I pick a number bigger than this, well, what's a number bigger than the cube root of 500 over pi? Well, you might say, you know, Kevin, I don't know what the cube root of 500 over pi is, nor do I, by the way. But I know a billion is bigger than that. So what am I going to pick? I'm going to pick a billion. I'm going to take a billion and I'm going to say, well, a billion is bigger than this. If I put a billion in here, I've got 4 pi times a billion cubed, I'm taking away 2,000. I'm pretty sure that when I put a billion in there, a billion cubed times 4 times pi is going to be bigger than 2,000. So this is going to be plus. What do I need? I need a number smaller than the cube root of 500 over pi. Again, I don't know what the cube root of 500 over pi is. But I know the cube root of 500 over pi is bigger than 1. I'm sure it's bigger than 1. Pi goes into 500. Pi is 3, so that goes into like 8 times, something like that. I'm kidding. It goes into a few more than 8. Got to be at least 10. And so when I take the cube root of it, I'm going to get a number bigger than 1. So I'm going to use 1 as my other value. I put 1 in here. I get 4 pi minus 2,000. That's clearly negative. Sorry, not 0. And so what do we have? We have a negative here. We have a positive here. This function is going down and then up. So this is a local minimum. Right? So on an exam, if you don't have a calculator handy, you can't plug numbers in. You can always pick numbers that make sense. Right? You have the ability. You know the number line way better than you think you know the number line. I agree. I don't know what the cube root of 500 over pi is, but that didn't hold me back. That didn't keep me from running my Sine Test. I just needed to think clearly about who's bigger than that and who's smaller than that. All right, so there's our second example. The questions say, find the dimensions that will minimize the cost of metal to manufacture the can. We have found what the radius should be, right? We know the radius for our can. How would we then find the height? We would take this and plug it into here for r squared, do our required arithmetic, and work out what the height should be, right? I think when we get all done, the height turns out 2 times r. If memory serves, I've done this probably a few times in class, but I'm I'm not going to do the arithmetic here. You can push pause on the video, as you probably should, and put this in for R here. Do the arithmetic and see if you get 2R over there for H. All right, so that's our second example. Let me erase this, and then we'll move on. We'll move on to our third example. Is the most exciting part of these videos the erasing? You didn't have to say yes to that. Kind of hurts. Every time I do this, I feel like I should ask you, do you want double rice? All right, there we go. Now I'm hungry. All right, so what are we going to do for our next example? Well, we're just going to, like I said, I'm going to do 4 examples here. I'm going to do, the first 2 I've done are classics. I'm going to do 2 more classics, and then we're going to call it a day. And let you go off and try to do some of the problems in your book. And hopefully these examples will be things you can come back to and say, oh, I see what you did there. I can use that in the problem I'm about to I'm trying to solve over here. Remember the steps though. The sketch is important. Write down what you're given, and it's always good to write down what they ask you to do. So what does this next problem say? It says we have a parabola, y squared equals 2x, right? So we have y squared equals 2x. One of our famous sideways facing parabolas, right? Y squared equals 2x. So it goes off like this and goes like this. And it says, for this parabola, find the point on the parabola closest to the point 1, 4. Right? Well, 1, 4 lives up here. This is 1, 4, right? And they want us to find the closest point on this parabola to the point 1, 4. Now, we know where that point is, right? We know if we draw a perpendicular line from there to the parabola, the line, of course, wouldn't be perpendicular to the parabola, but it would be perpendicular to the tangent line of the parabola, throw a little calculus in there. And that point right there, whatever that point is, that point right there, x, y, that point is going to be the closest point to the point 1, 4. Now, when we look at this problem, and it says find the point closest, right? Our job is to think back to our prior mathematical experiences and ask ourselves, well, what is it that I've learned in the past that might have something to do with me solving this problem? They want us to minimize the distance between here and there. I think if we just say that to ourselves, we can probably come to the conclusion that this right here might have something to do with our solution to this problem. That's supposed to be a 1, isn't it? That's where the 2 goes. It goes up there. There we go. That's the distance formula. Now, before everybody panics and looks at the distance formula and realizes it has a big square root in it, I'm going to point out something. If I square both sides, the square root goes away. If I square both sides, this turns out to be e squared equals, and over here I have x sub 2 minus x sub 1 squared plus y sub 2 minus y sub 1 squared. This is what we get if we square both sides. Whenever we're asked to do an optimization problem, and they ask us to find the minimum or the maximum distance, well, in this case, they would never ask us to find the maximum distance. The parabola goes on and on forever. It's kind of difficult to find the maximum distance. But if they want us to minimize the distance, we want to use this version. Use this form of the distance formula. And what is our thinking behind that? Well, our thinking behind that first is there's no square root. But second, the smallest distance is also going to be the smallest distance squared. If the distance between point A and point B is 10, and the distance between point C and point B is 12, 10 squared is smaller than 12 squared. So if I find the distance squared and make that the smallest, whatever I get for my answer there is going to be the smallest distance itself. The logic allows us to use this version of the formula instead of this version of the formula, which allows us to eliminate the square root, because we know we're going to end up taking the derivative, and we don't want to have to take the derivative with a radical. We would rather take the derivative without a radical. So that's my first hint when doing distance problems with optimization. So how are we going to move forward? Well, it says we want to minimize this distance, or we want to minimize, in this case, this distance squared. How are we going to do that? Well, we're going to write out what we know, right? We have values right here for the values of x and the values of y, so we know right now our formula looks like this, right? It looks like e squared equals our x minus 1, right? X minus 1 squared plus, and over here we have y minus 4 squared. Now, if we take a quick look at that formula, right, we could expand those. Everybody can FOIL, and, well, you can FOIL. I'm not sure I can. We'll find out in a minute. But we can try to FOIL these out. The problem we have is, once again, we've written down our equation, and we notice that we have to, right, we have to eliminate a variable. If we didn't get to this step when we were doing an optimization problem, that's when we have to tell ourselves when we're taking a test, taking a quiz, doing our homework, I think I might have done something wrong here. Houston, we have a problem, because if you don't have a variable to eliminate, it's either you're doing problem number 1 in the book, or you perhaps made a mistake. So where am I going to go from here? Well, I have x and I have y, and I can choose whichever to eliminate that I want. I can eliminate x, I can eliminate y, but I have to eliminate one of the two. Which one am I going to eliminate? Well, all the way back here at the top, they give us our given. Our given says y squared equals 2x, or if we look at that, it says y squared over 2 equals x. So perhaps we might want to eliminate, right? We might want to eliminate the x. We can instead replace the x with y squared over 2. Now, we could eliminate the y. You could take the other option, right? You could write this as y equals the square root of 2x. I'm not so sure that's the best choice. If you don't have to introduce a radical into the problem, why introduce a radical into the problem? So I'm going to choose to eliminate the x. And I'm going to rewrite this as d squared equals, and then in place of the x, I'm going to put 1/2 y squared minus 1. Now I'm going to have to square that. Plus over here, I'm going to have y minus 4 squared. Now what are we going to do at this point? Well, at this point, we're going to FOIL. 1/2 y squared times 1/2 y squared is 1/4 y to the 4th. Right? 1/2 times 1/2 is 4. The y squared times y squared is y to the 4th. Now what do we get? We get minus, and we get double this, right? So we get 1/2 y squared minus another 1/2 y squared. That's going to be minus a y squared. 1 times negative 1 times negative 1 is 1. What do we get over here? Well, we're going to get y minus 4 squared. And that's going to give us a plus, right? A plus here. And we're going to get y squared minus 8y plus 6. Now if we collect all of our like terms, we're going to get 1/4 y to the 4th here. We don't have any y cubed. We do have a y squared here and a negative y squared here. Let's just go back and make sure that's indeed what we were supposed to get, and it is, right? That's what we're supposed to get. So that's really nice. So we get 1/4 y to the 4th. We get negative y squared plus y squared. So we get a minus 8y, right? That's our next term, minus 8y. And then we have plus 17. Now, if we take a look at this, we only have one variable. So what are we going to do? Well, when we one variable, we're going to take the derivative, set it equal to 0, and hope something good happens. So what does it look like when we take the derivative here? What is it going to look like? Well, we're going to get the derivative of this, right? Whatever that is. D squared, we're going to take your derivative. And when we do that, we're going to take the derivative of this. So we're going to have 1/4. We're going to bring down the 4, right? We're going to have y cubed. We're going to have minus 8. The derivative of 17 is 0. And so what do we end up with? We end up with y cubed minus 8. Y cubed minus 8. Now, we know where we're going to go from here. We're going to set the derivative equal to 0, right? This is the derivative we're finding. The derivative of d squared. We're going to set that equal to 0. That's going to give us y cubed minus 8 equals 0, or y equals, in this case, 2. Now, what about when does y cubed minus 8 fail to exist? Well, we could write it down, right? We could write that down. Maybe our instructor says, well, I want you to show me that you understand that's a possible case. But in this case, it's because this is a polynomial, and polynomials never fail to exist. So, what do we have? We have y equals 2, right? Y equals 2. Now, looking at our picture, we ask ourselves, does that make any sense? More importantly, is that going to be a min or a max, right? Is that going to be a min or a max? So we could run the first derivative test over here. We have the derivative right here, right? We have the derivative. So what do? We could put down our 2 here. We could run our sine test, right? Run our sine test. Here's 2 as our choice. Now, right now our derivative is just y cubed minus 8. I know that factors, all of us who took algebra 1 can factor y cubed minus 8. But we don't have any other factors, so we can just write that down. Now we need somebody, right? Somebody smaller than 2, we can pick 1. We need somebody bigger than 2, we can pick 3. If I put a 1 in here, I get 1 cubed minus 8. That's going to be negative. If I put 3 cubed is 27. 27 minus 8 is positive. And so I get a negative on this side of my critical number, and I get a positive on this side. And once again, this is a local min. And that's what they asked us to do. They asked us to minimize. Wow. One thing the guy said at the beginning of this video was to write down your problem. We're just going to write this up here and act like it was always there. Yeah, see, it's been there the whole time. So this is a local min. We were asked to minimize the distance, and so at least so far, it looks like we're on our way to finding the answer. However, we have to make sure we read the problem, right? The problem says find the point on the parabola that minimizes the distance. That's what they asked us to do. Right now, we haven't answered the whole question. They want the point on the parabola. All we found is y equals 2. Now, where are we going to go to find x? Well, we have a formula right here that will help us find x. X is equal to y squared over 2. 2 squared is 4, divided by 2 is 2. Right? So our point that minimizes the distance is the point 2, 2. All right. So there's our third example. We'll do one more, and then we'll close out this video. Try to keep it under an hour here. Nobody wants to watch optimization videos for an hour. Let's be honest, nobody really wants to watch optimization videos at all. So let me erase this. I could just leave it like that, but, well, I have some students who do not appreciate that. So let me just put some of the magic spray on here and get this looking a little better for you. Alright. So we'll do one more example. This last example is, it's one of the kinds of problems that usually drives my students crazy because it comes with just one sentence. The whole problem, we'll even write it out at the top of the board here. It says, find the area of the largest rectangle That's the whole problem. And I don't know if it's a lack of information that drives students crazy. I don't know if it's the idea that we're back to geometry and we're inscribing things inside of other things. But I'm just going to start and point out some of the things that we need to know, right? We're trying to maximize area. And unlike the other example, we'll actually write it down in the beginning. All right, so the first thing we need to do is maximize area. And on top of that, we need to know R is a constant. This is so important when working on one of these kinds of problems. We know our semicircle has a radius of R. Okay, they told us that. R is the radius. They could have just as easily have told us the radius of our semicircle was 10, but they didn't. They said the radius of our semicircle is R. So R is the radius of our semicircle. So R is a constant. When we start building equations, we have to remember, unlike the second example where R was our variable, we were working on that cylinder and R was the radius and it could change. Here R is a constant. Okay? We have to keep that in mind. Now, the other thing that we have to keep in mind when working on a problem such as this, the sketch is the key. You want to make sure that you lay this semicircle out in such a way that you're going to be able to find the simplest set of dimensions possible. What do I mean by that? Well, we have a semicircle, the radius is R. There's no reason to just let this semicircle sit out in space. If you've told me that I have a semicircle and the radius of my semicircle is R, then the logical place to put my semicircle is to draw it, that's great gravity, but we'll act like it's a semicircle, is to draw it so it's centered at the origin. Because then I know the equation of this semicircle. This is x squared plus y squared equals r squared. That's the equation of our circle. So that's the equation of a circle centered at 0 with a radius of r. We want to make sure we set our semicircle in the most favorable position possible. Now, when we draw our rectangle, right? We draw a rectangle. Our rectangle is going to be inscribed. Remember, that means the corners of the polygon are going to touch the shape. So it's going to look like this, right? This is going to be our rectangle. Now, we know where that corner is located. That corner right there is the point xy. I don't know what x is, and I don't know what y is, but I certainly know this dimension right here is x, and this dimension right here is y. By the same argument, by the way, this dimension here is x, and this dimension here is y. Now, we're back. That's the sketch we need. We're going to go over here, and we're going to attack the problem now. The problem is just maximize the area. And it's not the area of the semicircle, right? We know what that is. It's the area of the circle, pi r squared, divided by 2. But we want to maximize the area of the rectangle, So we know the area of a rectangle is length times width. Now, in the context of the problem we're working on here, what's our length? Right? What's our length? Our length is an x. Our length is x on this side, and again, x on this side. So our length is 2x. Very common mistake made by students here is to write the length as x. The height, however, right, the width, in this case, the height, the width, that is y. So here we sit, staring at our problem. We have it right here in front of us, and we have our length is 2x, and our width is y. Okay? Now, what's wrong with this equation? Well, the same thing has been wrong with all of the equations. We have to eliminate a variable. Now, we have a place to go to eliminate a variable. Right here, we have a place to go, all right? We know that x squared plus y squared equals r squared. That's Pythagorean Theorem, or it's the equation of the circle, whatever you want to call it. You get the square root of both sides and call it distance formula, they're all the same thing. What do we know from this, right? What do we know from this? Well, we know if we take a look at this, we can solve this, right? We can solve this. We can rewrite this as y squared equals r squared minus x squared, or y equals the square root of r squared minus x squared. Now, unfortunately, we're not going to be able to eliminate having a square root in our equation that we're ultimately going to take the derivative of. We're going to come over here and we're going to say, okay, area is equal to 2x, right, times y, and for y, we ended up with the square root of r squared minus x squared. As much as we'd like that square root not to be there, it's there. We're going to deal with it. We're going to take the square root. We're going to take the derivative, and you know, we're going to work out what is the derivative of this. So how are we going to find the derivative? Well, we're going to find the derivative using the product rule, right? We have a function here, and we have another function there. In an earlier video, I told you Erwin Kramer helped me learn how to make those. He did, so shout out to Erwin. So what are we going to do here for a prime? A prime is going to equal the derivative of this, that's going to be 2, right, times the square root. Now, because we're going to end up having to factor this, I'm going to go ahead and write that as r squared minus x squared to the 1/2. So derivative of the first term, 2, times the second, plus first term, right, 2x, times the derivative of the second. And that's going to be 1/2 r squared minus x squared to the minus 1/2, right, the minus 1/2, times the derivative of what's inside. Now remember, we wrote it right here, r is a constant, so we take the derivative of r squared, we get 0. The derivative of this is going to be minus 2x. Minus 2x. All right. So if we simplify this, what do we get? We get 2. We get r squared minus x squared to the 1/2. Over here, this 2 and this half take care of each other, right? We get minus. And now what do we have? We have an x squared, right? A minus 2x squared. And then we have r squared minus x squared to the minus 1/2. Now we're going to have to set this equal to 0 and see where it fails to exist. Now, to do that, we're going to have to factor. So what can we factor out of this, right? We're going to do some more fancy algebra here. We got 2 comes out. We take out an r squared minus x squared to the smallest power. R squared minus x squared. The smallest power between 1/2 and minus 1/2 is minus 1/2. Right? That's the smallest power. Now remember, when you factor something out, you're subtracting that power, right? That's what you're doing. You're subtracting minus 1/2. We're subtracting minus 1/2. A lot of us struggle when we factor negative exponents, but if we would just write this step down, like I did right here, just write it down. If you do that, you almost always get them correct. So what do we do here? What do we have left? Well, we've taken out the 2. We took out an r squared minus x squared to the minus 1/2. So we have 1/2 minus minus 1/2. That gives us an r squared minus an x squared to the first power. Right? Half minus minus, that's 1. What have we taken out over here? We took out the 2. We took out r squared minus x squared to the minus 1/2. So we have minus 1/2 minus minus 1/2. That's 0. So all we have here is minus x squared. Minus x squared. Now what is that going to look like when we get done? Well, when we get done, that's going to look like this. 2. This is in numerator. So that's going to be an r squared minus 2x squared, right? And in the denominator, we're going to have this term right here. R squared minus x squared to the positive 1/2 because we dropped it to the bottom. Now, we all know where this is going to go, right? We all know where this is going to go. We'll just move over here. We're going to take a prime. We're going to set it equal to 0. And we're going to ask ourselves, okay, when is this 0? Well, fractions are 0 when the numerator is 0. So 2 is not going to be 0. So it's going to be 0 when r squared 2x squared is equal to 0. Now remember, r is a constant, right? We've written it here, checked it twice. So what do we have now? We have 2x squared equals r squared, or we have x squared equals r squared over 2, or we have x equals the square root of r squared over 2. The other option, of course, is to figure out when a prime fails to exist. We do have a fraction, and since we have a fraction, we can think to ourselves, well, Kevin, that fails to exist when the denominator is 0. So the denominator is going to be 0 when r squared is equal to x squared, which means r is going to equal x. Well, what does that mean? That means x would actually be equal to the radius. Well, if x is equal to the radius, we have no height. We don't have a rectangle. So this is an NA situation. So this is our critical number. Remember, r is a constant here. R is a constant. Now, we're supposed to maximize area. So how are we going to show somebody that that's actually a maximum? Well, we can run the sine test, right? If we run the sine test on that, we would be able to show that that is a maximum. We've done the sine test 3 times. I'll leave that to you. Now, the problem did say, though, right? The problem did say find the area, right? That's what we were asked to do, find the area. We should probably do that, right? We haven't done that yet. All we found is the radius. So how are we going to find the area of this rectangle? Well, to find the area of the rectangle, we're going to use the formula, right? Now, we're not going to use this formula here necessarily. This formula has a y in it. We'll just use this formula. We have x here. So what are we going to get for our area, right? What is our area? It's root 2 times x, which is the square root of r squared over 2, right? I kind of carried away there with that radical, didn't it? Times what? Times the square root, right? Times the square root of r squared minus x squared. Well, x squared is r squared over 2. So we have an r squared minus a half of an r squared. So that's 2. We've got this radical here. We've got r squared over 2. Over here we have a whole r squared minus a half of an r squared. Well, that gives us half of an r squared. Right? If we multiply those together, the radicals are going to go away, right? I don't even know what I just said. But if we multiply these together, what are we going to end up with here, right? If we simplify this, that's what I'm trying to say, simplify. Sorry, the words are getting harder. English, tough language for us native speakers. So this is a 2. If I take the square root of this, I get r over root 2. If I take the square root of this, I get r over root 2, right? And if I multiply root 2 by root 2, I get 2, and so we end up with r squared, right? So our final answer is r squared. That's kind of an interesting answer, isn't it? The area of the largest rectangle that can be inscribed in a semicircle of radius r turns out to be r squared. All right, I hope this video has helped you with your optimization problems. Hopefully when you set out to do your homework, remember, it's typical with optimization problems, very typical, that you write it down, you read it, you write it down, you read it, you write it down, and your first instinct is, I don't know what I'm doing. And that's fine. There's nothing scary, nothing wrong. You're human. That's a normal human reaction when learning. So when you get to that point, just take a deep breath, break it down into small steps, right? Everything is simpler when we make it into smaller steps. Step 1, what am I trying to do? Step 2, draw a sketch. Step 3, find my equation. There's going to be an equation out there that I know from elementary school. I know the maximum area of a rectangle is going to be length times width. Translate that equation. Based on your sketch, translate that equation. Don't panic when that equation has more than one variable. It's going to have more than one variable. 99% of the time, that means you're doing the problem correctly. Now take the given. There is a given out there. There's something. I like to call it the Easter egg. You just got to go find it. You got to go on that Easter egg hunt. Find that Easter egg. And once you find that Easter egg, it's going to allow you to rewrite your equation in only one variable. And when you get it written in one variable, then you're going to have to fall back on all those derivative rules you learned in the past. And then you take your derivative, run your first derivative test, run your Sine test, which we did not do in this example, and then at the end, make sure you answer the question that's asked. Nothing more frustrating than to do all the work we did here in blue, and then to turn in your exam, get it back, and find out, hey, I did great for 90% of that problem. But I forgot to answer the question. So just in the end, take a deep breath, make sure you answer the question. All right. I hope this video helps you, and have a great day.